Okay, so sketch curve sine 2x from 0 to pi. So 0, pi, 2 pi. So at pi over 2, it's here, pi. This is regular sine. So when you divide by 2, x is divided by 2. So pi over 2 is going to be pi over 4. Pi is going to be pi over 2. 3 pi over 2 is going to be 3 pi over 4. And 2 pi is going to be, so it's like that. So that's sine 2x from 0 to pi. Pi. On a separate diagram, sketch cosecant 2x. So this is the reciprocal. I'm just doing it on the same graph, so x-intercepts become asymptotes. And then it's like this. And then maximum point. So max is at 3 pi over 4 negative 1. Min is at pi over 4 1. Asymptotes are 0, pi over 2, and pi. So tangent x plus cotangent x is, this is C, tangent x plus 1 over tangent x, which is tangent squared x plus 1 over tangent x. And we're going to cosecant. So cosecant, I'm just going to try this. So this is going to be sine squared plus cosine squared over cosine squared over sine over cosine. That's 1 over cosine squared times cosine over sine. So just looking back to what we want this to equal 2 cosecant 2x. So 2 cosecant 2x, which is 2 over sine 2x. See what we're doing here? We're going to work backwards. So 2 over 2 sine x cosine x, right? So we can just multiply this by 2, which is 2 over 2 cosine x sine x, which is 2 over sine 2x, which is 2 cosecant 2x. Okay, so if you ever get stuck, just start from the other end. Hence or otherwise, find the coordinates of the local max and min points on the graph of that. Tangent 2x, so tangent 2x plus cotangent 2x. So here, if this is 2x, this is 2x, this is going to be 2 cosecant 2 times 2x, which is 4x. Oh my goodness. Which is 4x. Okay, so then, what did we start with over here? So we've got cosecant 2x graph. So if we have cosecant 2x graph, we need to do that. We need to divide the x's again by 2, because we have this graph, and if we want this, we need to do the transformation on that. So if we divide this to So, and this is 0 to pi over 2. So 0 divided by 2 is still 0. This is at pi over 2 divided by 2, which is pi over 4. This was pi over 2 here. Then pi divided by 2 is pi over 2. So what are we looking for? Okay, so those are the asymptotes. Now we have this minimum here was at pi over 4. So if we divide that by 2, that's pi over 8 here. But we're also multiplying by 2. So it was at 1. So that's going to be at 2 up here. So that is the new min at pi over 8, 2. And the max down here was at 3 pi over 4. So if we divide that by 2, that's 3 pi over 8 here. And then we need to multiply that by 2 because of this. So it's going to be 3 pi over 8 negative 2. Okay. Find the solution to the equation cosecant 2x equals 1.5 tangent x minus 0.5. Okay, so if we have cosecant 2x, so that was tangent plus cotangent over 2. Okay, so tangent x plus cotangent x equals 2 cosecant 2x. All right, and we want cosecant 2x. So we're going to have that is 1/2 tangent x plus 1/2 cotangent x. That's cosecant 2x. Okay, so that's that. This is going to equal 1.5 tan x minus 0.5. All right, so now we're going to have 1 over 2 tangent x equals, subtracting that, that's just going to be 1 tangent x minus 0.5. So if we multiply by 2 tangent x, so minus tangent x, okay, and then we have tangent x, 2 tangent x, 1 and 1. So we need positive here, negative here. So tangent equals 1 or negative 1/2. So here, x is, what is the domain? 0 to pi over 2. Okay, so this one's no solution, but this one's pi over 4. All right, consider this function from negative 2 pi to 2 pi by observing the graph. State its period and prove that it's periodic. That is that. Okay, so we have to graph it. So I just graphed it. One max is at 0. The next one's at 6.28, which is 2 pi. So the period is 2 pi. All right, and prove that it's periodic. Okay, so if we substitute in x plus t, which is 2 pi, we need to show that it gets out c at x, okay? So this is cosine x plus 2 pi plus 1/2 cosine 2x plus 4 pi. When you distribute that 2. So then this is cosine x, cosine 2 pi minus sine x sine 2 pi, which goes away because sine 2 pi is 0, plus 1/2 cosine 2x cosine 4 pi minus sine 2x sine 4 pi, which, whatever, it's still 0. Okay, so cosine 2 pi is 1, so this is cosine x, plus cosine 4 pi is 1, so this is 1/2 cosine 2x, which is equal to c at x. All right, so A. Now B, for what values is c a maximum? Well, it's going to be at negative 2 pi and 2 pi and 0. Oops. C, let x be x sub 0, be the smallest positive value of x for which c at x equals 0. Find an approximate value of x of 0, which is corrected to. So just do the 0 on the graphing calculator. It's 1.2. All right, D, prove cx equals c at negative x. Okay, so let's do c negative x. So we've got cosine negative x plus 1/2 cosine negative 2x. So just here, cosine negative x is equal to positive, cosine positive x. And same thing here. And this is equal to c at x. All right, double I. Let x be x1. And, okay, so in the graph, this second x-intercept, because the graph looks kind of, so here's 0, here's 2 pi, and then it's like something like that, whatever. So this is x0, this is x1. This is symmetrical. So this distance here is 1.2. So is this distance. This is x0. So if we do 2 pi minus x0, that's x1. All right, we've got this function. It can also be expressed like that. By expanding that and comparing with the original form, find the exact value of r and of alpha. Okay, so we've got r, and then we've got cosine x cosine alpha plus sine x sine alpha. And this is going to be equal, well, okay, so then this is going to be equal to cosine x plus root 3 sine x. So we've got sine x here. So that means sine alpha is equal to root 3. This is equal, actually r sine alpha is equal to root 3. Yeah? Okay, and then we're going to have cosine x so we're going to have r cosine alpha equals 1. That's its coefficient. So that means sine alpha is root 3 over r, and cosine alpha is 1 over r. So if this is alpha, we have sine is opposite over hypotenuse and cosine's adjacent over hypotenuse. So we've got root 3 squared plus 1 squared equals r squared. So that's 3 and 1, 4. So r is 2. And so r is 2. And then we need, so if this is 2, so we will have sine alpha is root 3 over 2, and cosine alpha is 1 over 2. Okay, so there at pi over 3. So that means alpha is pi over 3. Okay. State the period of f. So that means f at x is now r cosine x minus pi over 3. All right, so the period is just still 2 pi because it's 1 here. 2 pi over b, and the range is, so this does nothing to the range, but this makes it from -2 to 2, because it's usually principal axis is 0, and then it's usually amplitude 1, so up and down 1 from 0, but now it's stretched to 2. Okay, so that's b, I, and double I. And then c, find the exact value of x in 0 to pi over 2, satisfying the equation. Equals root 2. All right, so now we've got cosine x minus pi over 3 equals root 2 over 2. Our domain is 0 to pi over 2. And we need to subtract pi over 3. And pi over 2 minus pi over 3 is pi over 6. Okay, so cosine is root 2 over 2 at negative pi over 4. Okay, because we're from negative pi over 3 to pi over 6. Actually, yeah, it's not going to be pi over 4 because pi over 6 is less than that. So we're going to have negative pi over 4 plus pi over 3, which is going to be 12 negative 3 pi plus 4 pi, which is pi over 12. Okay, 23a. So we're going to have cosine A cosine B minus sine A sine B plus cosine A cosine B plus sine A sine B, which that clearly cancels, so we're going to have 2 cosine A cosine B. B. Let t be that, where x is a real number between -1 and 1, n's a positive integer. Find t1. So cosine 1 cosine inverse x. So that's equal to x. Okay. So t2 is cosine 2 cosine inverse x. So if we have this old trick, theta's cosine inverse, this is going to be cosine 2 theta, and then that is, and look where we're going, so we're going to do 2 cosine squared theta minus 1, and x is cosine theta, so cosine squared theta is that, 2x squared minus 1. All right, C, use the result in part A to show, induction. All right, Tn plus 1. So, Tn plus 1 is cosine n plus 1 cosine inverse x. plus cosine n minus 1 cosine inverse x. Okay. So cosine distribute. So we're going to have n cosine inverse x plus cosine inverse x plus cosine n cosine inverse x minus cosine inverse x. Okay, so we have cosine a plus b, so from a, we want to use this thing. So this is clearly a, this is a, and this is b. So we're going to have 2 cosine n cosine this b, cosine b. Okay, so just a second. So this bit is x. So that is 2x. And this bit is t. Yep. So that's that. Oh man, 12 marks here. So, prove by induction, t sub n is a polynomial of degree n. Okay, just to go through the whole process again, we're going to have show true for n equals 1. So that is what we did here. So cosine of the cosine inverse of x equals x. Okay? So x to the 1. So see, n is 1. And it's also degree 1. Okay? So now we assume true for n equals k. So t sub k of x is going to be cosine k cosine inverse x equals x to the k. All right, so then we're going to show true for n equals k plus 1. So now we have this bit. So the way that they do it is, because we want to show it's true for the k plus 1, we're assuming it's true from 1 to k. So we can also assume true here for n equals k minus 1, so before k. So tk minus 1 x is equal, so it's going to have x to the k minus 1. So we want to show this one is x to the k plus 1 here. So remember, t k plus 1 of x plus t k minus 1 of x is equal to 2x t sub k of x. That's from CI with k. All right, so this one, tk minus 1, this is going to be x to the k minus 1. And this one's 2x, and this is going to be x to the k. All right. So now, k plus 1. This is going to be 2x to the k plus 1 minus x to the k minus 1. And if we factor out x to the k plus 1, that's going to be 2 minus x to the negative 2. So when you add the exponents, it's going to be k minus 1. So t sub k plus 1, x has degree this since this is the highest degree in the polynomial. So it is true for n equals 1, and when n equals k, it is true for n equals k plus 1. It is true for all n by PMI.